In this video, I'm going to introduce truth tables. Truth tables are a convenient way to represent a logic equation or a digital device. Now here's an example of a typical truth table, and it has a few components that you should be aware of. This top row right here is the name of all the inputs and outputs that you have in your logic device or your logic equation. And so each of these individual columns represents a different input or output. And the inputs are over here on the left, and they're separated from the outputs by a vertical line that you can see right here. So then the outputs are always on the right. Now, the heart of the logic is stored in the rest of the truth table in these false and trues that you see here, represented by F's and T's. Now, the false and trues can also be represented as ones and zeros. A truth table has to be able to account for all the different possible inputs that can go into the system. And this can be achieved by simply doing some binary counting on the inputs. So as you can see, if you treat A and B as two different bits of a single digital number, then you can have 0, 1, 2, and 3. And so for each of the different possible cases, we need to define some output C. And that's what's done over here on the right-hand side. And so in the end, this truth table just represents what happens if you have some digital device with inputs A and B and output C. If we let A equal 0 and B equal 0, then we know from the truth table, we go to this row right here, that C is also going to equal 0. Alternatively, if we let A equal 0 and B equal 1, then we come read this row of the truth table, and we find out that the output is 1. So let's figure out the truth table for a few common logic operations. First, and most simply, is the NOT operation. And so we know that the NOT operation simply inverts whatever the input is. And so NOT would look something like this, where we have A coming in and A prime coming out. And so quite simply, we just flip the bit of whatever goes into the input, so false becomes true, and true becomes false. Next, the OR logic operation. We know from Boolean equations that OR gives you a true result whenever either A is true or B is true. So in this case, that means that it is only false if they are both false. In all of the other three cases, we have a true result. Finally, the AND operation, A and B. And we know that A and B is only true if both A and B are true. And that's this final case right here. And so we know that's true, but then all the other cases are false. So once we have a truth table that describes the overall logic of a system, we might want to be able to convert that to a logic equation and ultimately to a circuit design. Let's say we have this truth table. This is the same one we started with at the beginning of the video, where we have two inputs, A and B, and an output, C. So in order to convert this to a logic equation, first we have to write an equation for each output. And so here we have a single output, so we'll have a single logic equation. Next, we have to find all the rows where the output is 1 or true. And that's just these two middle rows right here. So these are the two rows we're going to focus on. The third step is to write the product of the two input cases that lead to these trues. So this first row gives us A naught and B. Right? So that's this operation right here. And then this second row gives us A and B naught. So there's a 0 here, so that's why we use the B naught instead of the B. And then finally, we just OR each of these different terms together. So you'll have a different product, or AND, for each individual output where the output is true. And each of these products will consist of all of the inputs. Now these AND operations that combine all of the different inputs have a special name. These are called minterms. And we'll learn more about these when we use truth tables to optimize the logic for an efficient circuit design.